Okay. Yeah. So I'll recap logistic regression, maybe 5 minutes to remind you. But before, as a warm up, let's do some hands-on activity. Let's say I got a continuous random variable x, and somebody comes in and says, okay, I define another one, y, which is 2 times x plus 1. You know, very simple, right? So I take your random variable, I multiply it with 2, I add 1 to it. All right, now the question is, what happened to the density? So can you work out the density of new random variable y in terms of the density of x? Okay, please get going. Try your best, we'll do it together. But it's always better if you try. So, if you just to remind you, we had cumulative distribution function, then density was its derivative. You can reason through both. Like I could also walk around and bounce off ideas with you guys too. All right, let me give you a minute to think about it. At least then I can stop watching. It's much more advanced than this. I'm asking you a very simple question. Like, take your random variable, multiply it with 2, add 1 to it. You know how the change happened precisely. Now, what happened to the density? That's what I'm asking. The stuff you say looks a lot more sophisticated than what I'm asking. Not sure. Okay. Yeah. Okay, let me maybe write some simple stuff. So what was the definition of like cumulative distribution function thingy? Maybe let me start from there after I manage this wire spelling. All right. So what was that cumulative CDF type stuff? FXT, the definition was, or maybe let me start from Y's. Yeah, right. It was Y less than T, right? And the density of Y was literally take derivative of this, you will get it, right? That's what it was. Okay, good. So far, I guess this is the stuff you knew from last lecture or the lecture before. Okay, you write the cumulative thingy, then take the derivative of it, you got the density. Cool, so what is Y? Let me put that in. So Y is 2x plus 1. Okay, probability of 2x plus 1 being less than or equal to t, I can move things around. This would be the same as 2x less than t minus 1, for example, right? Or I can move it and divide by 2. I can manipulate things. So this would be probably the same as, let me see. First, put the 1 right-hand side, t minus 1, then divide things by 2. Tx less than t minus 1 over 2. Doesn't make sense so far? Right? I moved the 1 right, and then I divide by everybody by 2. But okay, then what is this? X less than or equal to t minus 1 over 2. This is again something about the cumulative distribution function of x, but not computed at t on somewhere else, on t minus 1 over 2, right? Okay. Using the advantage that I could move it to the left. All right. This would be f cumulative x t minus 1 over 2, right? So far, so good. Okay, now I'm going to take derivatives left and right. So derivative of this guy will give me the density of y. derivative of this should give me something about the density of x, one way or another, right? Okay, on the left-hand side, t is derivative of this. Then I take derivative of fx at t minus 1 over 2. What is that going to be? So now, here I'm taking a derivative of a function, cumulative distribution function, but inside there is actually one more function. Inside there is not a t, there is like t minus 1 over 2, right? So you guys remember your chain rule from calculus. So I'll remind you that because this is going to keep showing up as whenever you're doing neural nets, back propagation, you're doing chain rule. So we better be in peace with that thing. Okay. So let me remind you the chain rule thingy. If I have two functions g and say h, and I have x, if I'm taking derivative, it looks like this: g derivative hx times h derivative x. Okay. This is like the general chain rule. If h is put inside g, when I'm taking derivative of two functions on top, take the derivative of the first one, put your hx in, then take the derivative of whatever you put inside, put your x in there, okay? For us, I'm taking derivative of this at this point. I know what is the derivative of this. It's literally the density, okay? So I'm gonna write first this here, derivative of this, let me write, which is the density. Then inside, you see I'm putting hx, not x. For us, that h is the function that takes t, then minus 1 divided by 2. That's our function. Okay, so I'm going to put t minus 1 over 2 here. Let me scroll up a little bit. And what is the derivative of t minus 1 over 2 in terms of t? Just half, exactly. So that's our answer now. Do you need this chain rule, or can I erase it? Or maybe let me put it up there. This is just chain rule. Let me put it in a different color. So now we figured out our answer. Turns out the density of y is the density of x evaluated on a different place times half. Okay. Of course, there was a purpose I started with this exercise. You realize to create y, we multiplied with 2. But when we compute what happens to density, the opposite happens. You're now dividing with 2. Okay. And why, right? Okay, so why is this happening? Yes, go ahead. Exactly. So very good idea. So, and actually I have a picture of what you just said. So here is what was just said. So thank you. That was the intuition. So I was between 0 and 1, but when I multiplied with 2, I'm now going between, say, and we also did a plus 1. Now I'm going between 1 to 3. The place I'm going, like, got lengthened by 2. But at the end, the area remains the same. The total area is always 1, right? So when you integrate the whole thing, it's the whole probability. It's always 1. So what does that mean? That means the density has to go half, because you're going to integrate over from 1 to 3, twice the length instead of 0 to 1. But you want to, at the end, get the same answer when you integrate over. It's going to be always 1, the total area. So that's why first it looks maybe a little counterintuitive. I was multiplying x by 2. Y density got divided by 2. That's the reason. The whole thing is always probability 1. What's the probability of every possible thing? 1. Fine. Well, you lengthened your range by 2, so then you're going to divide your density by 2. Okay? So far, so good? You guys are probably much smarter than I am. When I first saw this some years ago, it looked very weird, I remember. But then I got used to it. All right, so, and what else? There is like some more illustration about, so this 1 over 2 is what? Y was given by 2x plus 1. if you take derivative of x with respect to y, you will get 1/2. You can think about it that way too if you like. Okay. Okay, very good. Any comments about this? All right. You can do the same story multivariate. So for example, suppose you got n coordinates, that's your random variable. And then you go multiply it with a matrix, and you also add a bias, that's your new random variable, right? That's literally what we were trying to do with logistic and whatever, linear regression. That's kind of all we were trying to do when you do a linear model. You have some random variable, sometimes it's literally just uniform or Gaussian, whatever. Anyway, that's like a general thing that you'll keep seeing. And then now the same question, okay, what happened to the density when I go from Z to Y? Okay. I'll not fully work it out for you, but I want to give you the main intuition about this. And let's, for now, just look at the, okay, I can go one by one. The first picture is just like shifting. That's, if your matrix was identity, you're just shifting. And then, of course, you would intuitively think nothing is going to happen to the density. I'm just shifting. It's just the same shape somewhere else. Density remains the same. Fine. And now let's think about, I'm not shifting, but I take my shape, I multiply it with a matrix. To be precise, my shape was 0, 1, 0, 1, the square thing. This is my matrix. Okay. My x random variable was uniform between 0 and 1. Now I go multiply it with a matrix. What happens to everybody? If you look through, your 0, 1 square becomes this new shape. Okay. And then what's the area of that new shape? Exactly. So it looks like you had a good linear algebra teacher. Meaning of determinant is about the area of the shape spanned by the columns of that matrix. Literally, you get to go by the determinant of this matrix. Okay. Since it's getting enlarged by the determinant, you need to divide the density by 1 over the determinant. That's how it is going to go. Precise details, how you write it up doesn't really matter too much. If you want, we can write it up. But the main intuition is what was just said. The density gets changed by the determinant of the matrix you're multiplying your vector with. And the reason for it, determinant actually means the area. Sometimes in linear algebra classes, they give this horrendous Laplace formula as definition of determinant. Okay, that deserves punishment. But, I don't have the power to do that. But determinant, what it is, it's actually like an area, volume, that's what it is. It's a little more than just area and volume because determinant can be a negative number. Volume or area is always a positive number. Okay, so determinant also cares about how did you order those vectors. That's about it. Order plus area or order plus volume is the determinant. Okay, that's all I wanted to say about this stuff. If you really want to see, just look at the book. I just didn't want to spend time. It's called Linear Transformation of Random Variables. Yeah, so this is how you act on your random variable. You multiply with this matrix, then you can add a bias. How it reflects on the density is through determinant, and it's written explicitly in the book. So no worries, transformation of random variables. It's, yes, basically, yeah. Okay, you'll just see it there in detail, written very clearly. All right, okay, fantastic. So let's go back and recap quickly the logistic regression stuff, then we will move on to other things. Right, so where was my logistic regression? Yeah, we talked about logistic regression. So I told you this lifting trick. You can do logistic regression right away on your data, or you can lift them up. And when you lift and do, instead of linear boundaries, you will start getting these curvy boundaries. This we talked about. That's not what I'm going to recap now. I'm just going to recap what it is and how you make an interpretation of it. Okay, here is logistic regression. So this is a linear model for classification. You got your data points. They all have D features. And they are going to have a label. And every label means a data point belongs to class 1 or class 2 or class n, whatever. Okay. So we have a notebook. It is only about the binary case, 2 classes. That's a very common case of logistic regression. And the notebook goes by the standard notation you would see here and there. You might not see always written it this way. So I'd like to go over it and explain the notation so you don't get confused. Okay, so basic model is this. You got a matrix and a bias vector. You take your data, you multiply it with your matrix, and then you add the bias. And this is now yet another vector. And you take that vector, you do softmax on it. And then after softmax, you turn it into a probability distribution by making it a categorical random variable. So how did the softmax look like? Let me go through it. So when I have this Wx plus b, and if, let's say, my W matrix is, let's say this is my matrix, first row, second row, dth row, right? Yeah, or wait a sec, nth row, I'm sorry. It doesn't have to have the same number of, okay, let's say this is n by d matrix, your data has d features, and your bias vector has to have n features as well. Okay, let's say this is my matrix. Every row has d features. I'm multiplying them with my data right here, okay? So let's put my data next to it. Let's say this is my data stuff with d features. And when you look at how w times x look like, let's say this is my data x here, it's got d features. The first one will be literally first row, dot product or inner product with x. Second entry will be second row, inner product with x. It goes like this, right? And then let me be lazy. Let me also add the b right here. Then I'll add the b stuff. This is how the output is going to look like, right? Take the first row, multiply it with your data. This is going to be a number now. And then you're adding bias p1 to it. That's going to be the first coordinate of the output when you do wx plus p. And then when you look at all those, this is what you got right here. Okay. Then now what's going to happen next? This is a vector with a whole bunch of numbers. We are going to do softmax on it. What did softmax do? So if your vector, say, was looking like, let me simplify my life a little bit. If your vector was like A1, A2, da, 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 AN, when you do softmax on it, what it does, it takes everybody to exponentiation and then sums up all the exponentiations and divides by it. Okay, this is what it does. Now it will take all this stuff, put them on top of exponents, divide by summation of all that exponents, okay? So the idea here is like if, say, the first coordinate was bigger than the second, when you do exponentiation, this is going to look much bigger than the second one. That's why it's like a soft approximation to maximum. Max will look through all the coordinates, pick the biggest one, okay? So this is almost doing that. And when you push it to the limit, it becomes max. Since we want to have stuff that is differentiable, when we do anything with neural net and whatnot, this function replaces the max operation, okay? All right, very good. This is how it is going to look like. And now at the end, what you want to do, if you fit your best matrix and best bias, you're going to put in your data, multiply with that matrix, put your bias, get your vector, put on top exponentiation, look at the biggest one. That's the highest probable class for your data to be belonging to. All right? Okay, fine. Now, there is one trick people would always play, and which is the following. Since I'm trying to compare all these coordinates, I can go pick one of them and turn that coordinate into literally 1. How would that be? Let's say, I don't know. Let's say somebody's favorite number is 2. Okay. Take this vector and multiply every coordinate by e to the negative 80. Take that softmax thing, multiply with this. What you're going to get, e to the a1 minus a2 divided by the whole sum. And let me give a name to the whole sum. Just not to write this over and over again. Let's call this guy star. Here your star. And then 1 over star. And then e to the a3 minus a2 divided by the same star. You see how this is going to go. Okay. And then now you lost no information by doing this. Because if this number is bigger than that number, the first coordinate is still bigger than the third coordinate. So if you do this careful, you'll lose no information doing this. And in the binary case where there are only 2 outputs, this trick is defaulted. In the binary case, you will always see the function that they will tell you sigmoid function. It's going to always look like this. Sigmoid of a number a will be 1. This, okay? And this is literally the second coordinate you are seeing there. If you have only one number. So this corresponds to following. E to the a divided by this. So it's okay. So that's why in the binary case, you will not see 2a1, a2. Normally, that's what the function is trying to do, trying to estimate probabilities of 2 outputs. You have 2 outputs. They'll just do this trick by default. They'll say, okay, I fix one of them to 1. I just estimate 1. And that's yours, okay? That's also what our notebook is doing. And that's some trick you will see all over the place. It's nothing different than what I told you. Just this kind of dirty trick is defaulted, okay? That's about it. So I was trying to say, let's say this one. I also did not do something terribly carefully. When I'm multiplying everybody with this, to keep the ratio the same, I need to multiply top and bottom. That's why you always get a 1 here. That corresponds to, it was e to the, say, a. You multiplied with e to the minus a, it became a 1. I'm sorry. Yes, let me write that out there. To keep the ratio the same, I'm multiplying top and bottom by e to the minus a2. Okay, so let's give a name. Okay, let me correct this. I'm sorry. So let's say star star is that star multiplied with e to the a minus a2. Okay, very good. Then the same expression here can be written as star 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 star. Yes, very good. Now, coming back to your question, Adam. Adam was happy with when I compare 1 and 3rd, say. I'm just going to still look and compare. How about 1st and 2nd, since I made it into 1? Okay. Now you are still going to look at if this is bigger than 1, which literally means if this is bigger than 0 or not. It's all good. since it's all fractions, you divide top and bottom with the same number, nothing changes. Okay, so this right here and this right there are exactly the same thing. I'm just showing you because it's how they write it by default. Sorry, this may look confusing. I'm just trying to save you when you look at the notebook or wherever else, when you see this and say, this doesn't look like at all what I saw in the class. That's why I'm showing you this, okay? And this thing is called the sigmoid function. And that is a approximation to maximum. And that's why this is used all over the place when you talk about multi-layer perceptrons. Okay. So you would see this sigmoid used as an activation function. Okay. You can also forget about the last comment I made. We will get back to that later. That's all, okay? You do Wx plus B. You try to fit the best W and D. You do softmax. You look and you say the biggest probability is my guess for classification. And when you look around, you will see this representation instead of that. That's about it. There is one more little detail. If you are gonna sit down and re-implement yourself from scratch, this is already implemented all over the place. But if you're one of those people who learns by implementing, when you do this, you need to be careful. This can become a very big number. There's a little trick that fixes overflow issues you could run into. It's called log exponentiation trick, explained in our textbook. You can take a look. It's a little dirty trick that saves you from overflow. Yeah, you basically log and get back something like that. That's about it. Okay, that's all I want to say about logistic regression. We have notebooks, and we spent quite a bit of time last lecture. I could have just moved on, but I didn't feel so good without explaining this trick, which is defaulted in all the places. Okay, that's about it. Any questions about logistic regression? Let me show you some nice pictures again while you think if you have a question. Everybody's good? No questions? Okay, if you have no questions, one little comment. As you see here, and we talked about last time, this is the pictures you see when you do that lifting trick. You take your data, you lift, as we talked last time. But as you see, if you keep lifting to higher stuff, this is degree 2. This means take features, do degree 2 stuff off of them. X1 times X2, X2 times X5, whatever. This is degree 4. This means take 4 features, X1 times X2 times X3 times X4. This is a much bigger lifting. And when you look at the performance, degree 4 does worse than degree 2 in this particular data. This orange spot is the error in test data. Blue is the error in training data. It's doing better and better in blue. After degree 2, it starts doing worse in test data. And as we talked last time, this is a sign of overfitting. Your thing captures your data very well, but does not capture anything else that it has not seen before. Right? And we will talk about the remedies to this type of situation, likely starting from next lecture and onwards. Okay, very good. Yeah, go for it. You mean like if I have features, say x1, x2, x3, you will go by x1 squared, x2 squared, x3 squared? Yeah. That particular one, I have not seen used so much. Because when you square it with itself, it's not necessarily capturing any relation between the features. You're still keeping every feature to itself, right? One idea in lifting trick is like, let's say if the first one and the fifth one is correlated, when I multiply them, I'll start seeing that correlation in my model because I got now x1 times x5. But if you only squared it, I think it will only Sometimes it will help you with numerical computation. Sometimes it will make it worse. And other than that, I don't see any statistical meaning. Not sure. Maybe show me, then I can take a look at. Yeah, show me, we can look at it together. And that's why office hours is there, to talk together. Yeah. All right. Thank you. Okay. That's about it. And let's keep moving. Okay. Now going back to probability, we talked about expectation, second moment, third moment, variance, standard deviation. Then we started talking about conditional expectation. So what is conditional expectation? If my second variable y is somehow related to x, when I know something about it, it changes my expectations about x. Suppose you know y is b, whatever that b is. How are you going to update your estimate for expectation of x? Instead of taking the density, now you will take the conditional density. You will say y is fixed to b, conditional density goes over all possible t values. I multiply them with the values t, I integrate over. That's the conditional expectation when you know the second variable is literally some number. You did the experiment, you know what the heck is going on with the second random variable. And sometimes you would see only x conditioned on y, then conditional expectation, where you don't necessarily know what is the particular value that is taken by second random variable y on an experiment. Then what would this mean? This means this is one level of abstraction from here. This means this is a quantity. It takes this value on the part of your universe when y is that b. For example, this will take expectation of x conditioned on y equals 5 here in this universe. And if you're in this part, it will take y equals 4, etc. This is one more level of abstraction, okay? Let me do an example for this to make sense of something this abstract. So let's say x is my geometric random variable. It has a success probability p. Let's say I'm trying to get out of prison in Monopoly or done whatever else. I want to get a 6 of my dice. That's my success. And I'm going to keep rolling until I get my 6. Okay, what's the expected number of rolls I will do? That's the expectation of geometric random variable, right? So what I don't know the expectation. What I know is like, what is the probability of getting the success in the second try? Well, first fail, then success in the second. What is the probability of getting your success in the 10th try? 1 minus p, failure raised to the power 9. You have to fail 9 times. Then in the 10th, you success. Okay, that is the description of my geometric random variable. But this doesn't tell me so much about what's the expectation. Okay, you can try to go ahead and compute expectation with the usual formula. If I would try to do that, it will look like this. What is the expectation? How do I compute it? I go through all values this thing can take. Theoretically, I can wait till infinity to get my success, right? So I'm going to multiply those values. Let me use the same k, maybe, not to change notation. K times probability of x equals k. And if you write it up, it will become this gigantic summation. K times p times 1 minus p, k minus 1. You can maybe do a lot of math and work this out, okay? But we will do something else. We will try to utilize this conditional expectation stuff. And how does that go? You first hook up a random variable that helps you unravel your complicated random variable. In our case, this complicated guy will be this, x. And now I have to cook up some y, okay? Here is a candidate, y, that you can try. Y is a new random variable. Let me think about it for a sec. It is 0 if x is 1. It is 1 otherwise. So what does this do? If you tried and you were successful at the first try, this is 0. And if you were not successful, it is 1. It's just a new cooked up random variable. And what's the probability of you being successful? P, not successful, 1 minus P, right? So it's easy to understand when this guy is 0, it happens with probability P when you are successful at the first shot, and 1 in all other cases. So far, so good. Now let's think about the conditional expectation. What is the conditional expectation of X based on Y? Well, if Y is 0, I know what is X. It's just 1. If Y is 1, what does that mean? I tried and failed in the first try. That's what it means. Now, what's your update for expectation? So let me maybe ask you a less abstract question. So if conditioned on Y equals 0, then your expectation is literally 1. Because you know that's what it means. How about this? You failed at first try, that's all you know. Exactly. So you take your expectation, whatever it was, I don't know what that is yet, but now it increased by 1. That's what I know. This is what I'm trying to compute. I don't know it. But what I know is like knowing the failure in the first shot increases my expectation by 1. I failed once, I'll keep trying. That's all about it, right? So far, so good. Now, let's put this into, yeah, question? Yes. So you don't know you're going to fail, you know after you failed. Hope that makes sense. So you'll get to where you're saying right now, okay? Give me a sec. But so far, does this too make sense? If you know your Y is 0, then expectation for X is just 1. If you know your Y is 1, expectation for X just got increased by 1. That's all, okay? Now, I'll use the fact that I presented last time, but it was quick. Let me remind you again. You can take an auxiliary random variable Y, anything you like, then your expectation will get just nested, okay? You will go through possible values of Y, and then take expectation of this, okay? So let me do that. So now expectation of X will become expectation over Y conditional expectation. And Y has 2 possible values, either 0 or 1, right? So this means probability of Y equals 0 times conditional expectation when Y equals 0 plus probability of Y equals 1 conditional expectation. Maybe let me put this plus more prominently. So now I know this thing equals to this thing. Does it make sense? I'm taking expectation over Y. What is the definition of expectation? Look at the values it takes, multiplied with the probability it takes that particular value, okay? So when probability of Y equals 0 happens, this thing inside takes this value, whatever that is. Does it make sense? Okay, then I'll just plug in the stuff and we will get our answer, okay? So now let me plug in stuff. That means expectation of X, probability of Y equals 0 was P. And this was 1. Probability of Y equals 1, 1 minus P. And this thing was the expectation plus 1, right? If this red is making things complicated, let me pull it up a little bit. So far, so good. I'm waiting, ask me questions. I'm just using this expectation being equal to this. Then for Y, I got only 2 possibilities. Probability of Y being equal to 0 times conditional expectation when I know it's 0, plus probability of Y being equal to 1 times conditional expectation when I know it's 1. Okay. Does this answer your question now? So you were asking me like, if I know I'm going to fail, blah, blah, blah. I do not know if I'm going to fail or not. I'm looking through all options. Yeah. All right. Now it's almost, like a basic algebra question. Call this, say, some variable A. A equals P plus 1 minus P times A plus 1. You can literally solve this equation and find your expectation of X. Yeah. Yes. This one, you mean? So this is correct for any Y and X, and you could keep nesting even more if you like. You can nest Y on a Z and put one more expectation, blah, blah, blah. And now the meaning of this is I'm taking this expectation over Y, and I'm taking expectation of this quantity. Okay. Then look for options for Y, probability of Y being 0 times this quantity when that happens, plus probability of Y being 1 times this quantity when that happens. Okay. Very good. And then you just solve this and it gives you the expectation. Its expectation equals 1 over P. If your success probability is P, the expected number of times you try is 1 over P. It's kind of intuitive. If your success probability was, say, 1 out of a 6, the expected number of times you expect to roll is 6. Right. But to compute it using the usual way on top wouldn't be that intuitive at all. You can do that math too. Okay. Going from this to 1 over P would require a whole bunch of tricks. It's doable, it's fun, but I'm just trying to show you how you can utilize this conditional expectation. For example, here is something that was a classic interview question. I'll put it as an exercise today, and some companies are going against brain teasers in interviews. So I'm not sure if it is still an interview question or not. It goes like this. I want to roll 2 number 4s consecutively. I'm rolling a dice. I just don't want a 4. I want 2 of them next to each other. 4 and a 4 again. What's the expected number of rolls I'll do? That's the question. So if I am looking for only the 4, now I know the answer. It's 6, right? It's a geometric random variable. If your success probability is P, it's 1 over P. To get the 4 is 1 out of a 6. Okay, I expect to get 6. And then you ask, what's the number of rolls you expect if you want to get 2 4s consecutively next to each other? People usually say 36. They multiply 6 times 6 in the head. And that's the wrong answer, of course. That's why it's a question. So this is trying to check if the candidate knows conditional expectation or not. I guess they still ask this if you go for finance type stuff. But in tech, I think it's a discussion now. If you ask this or not, I don't know. Some of my friends used to do interviews in Austin. Now they moved to Silicon Valley. They don't talk to me anymore. They got so rich. Okay, the second part was a joke, but they are not doing these interviews anymore. So I don't know the latest status. All right. That's conditional expectation. And as I said, I'll put what I just told you as an exercise. You don't need to remember that. That used to be a standard interview question. Okay, so far so good. Any questions? Very good. Now, I erased the title. We are switching gears. I erased the title to just create some space for my computations. The title was Summary Statistics for 2 variables, for 2 or more, let's say for 2 variables. Okay, sorry for that bad writing there. So we talked about expectation, variance, standard deviation, higher moments, conditional expectation. So far, it's all about just one random variable. How about you have a random variable which got 2 coordinates, like you have an x1, x2, and you want to think about them together. Okay, you could think about, say, expectation of x1 squared. You could think about expectation of x1 times x2, x2 times x1, x2 squared, and you could go on and on and on. You can also think about x1 to the 3rd, blah, 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 okay? For now, let's only think about this 4 stuff written here. if these two random variables are independent, x1 times x2 expectation will be literally equal to this quantity right here if they are independent, okay? If they're not independent, this could be a positive number or a negative number. Or this could be 0. When you get a 0, it doesn't mean independence, okay? So independence will make this 0. But when you get a 0, you cannot conclude they were independent already, okay? That means you just don't see it. Okay. Now, if you get a positive number from here, take this minus that, they will be called positively correlated. What does that mean? When I take them one by one and multiply the numbers, I get something smaller than taking them together. It's like these two random variables want to happen together. They're kind of correlated. That's why it's called positive correlation. If you get a negative number there, it's called negative correlation. And now they will usually not only look at that number, positive or negative, they will divide that number with the standard deviation multiplications to normalize it. Then you will get a more normalized number. It's called correlation coefficient. This final number now will be between 0 and 1, okay? And 0 would mean looking like independent. Doesn't show me some correlation, at least from this statistics. 1 would mean they almost look like, okay, almost the same random variable. That's how they behave. Terribly correlated, okay? So that's the lingo. And that's what you would see all over the place. When somebody tells you correlation coefficient, that's what they mean. Or positively correlated. So positively correlated is kind of a colloquial word. This is what is technically defined to be. But if you're in a meeting and somebody's saying positively correlated, you need to double check if this is really what they mean or not. Okay. So sometimes people use it just like colloquially. Okay, they seem to be positively correlated without really any technical attachment to the word. Or they might be very technical people. Maybe they mean more than what I just said. So you need to check. But this is the usual official definition of positive correlation. All right. Okay. Now, this is the lingo. Let me. So far, so good. Any questions? This is recorded. And this is standard stuff. Should be in the textbook. So if you couldn't write it down, don't worry too much. I can wait. Sigma means standard deviation. Standard deviation, first random variable times standard deviation of the second random variable. Yeah, very good. So it's kind of trying to normalize it to make it more sensible number. So far, so good. Okay, now what do we learn from this? This is the picture I showed you last time. It is cooked up to give you a warning sign. This is called Datasaurus because of the dinosaurs on top. So all these data points, the first coordinate is x1, second coordinate is x2. If I record it right from the source, which I'm not sure, the expectations are the same, standard deviations are the same, and the correlation coefficient is also the same for all this data, all of them. Okay. But as you can tell, they're not so similar data to each other. This is just a warning sign. If you take some data and just go off of the statistics you collected, it might go off the rail. So this doesn't mean to say that the statistics has no meaning. They do have a meaning. We will talk about that today and in next lecture, but they don't tell you all about it, basically. Okay. So eyebrows I'm trying to instill to you, like you should raise your eyebrows if somebody tells just two statistics and we understood everything about data. Remember this picture, okay? That's the first thing. And the second thing I'll try to tell you today, or maybe next lecture latest, if somebody says by central limit theorem, we can just use a Gaussian. That's the second thing you need to be careful about, which you will hear probably a lot. Okay. Okay. Both of them is meaningful. central limit theorem applied is meaningful, of course. This statistics also meaningful, but they don't really capture everything. Okay, so far that's about it. Let's keep going. So the real thing you want to actually understand is like the joint density, but this is usually more work. Okay, now we are slowly going towards like what do we learn from the statistics? Okay. One thing I want to tell you is called convolution theorem. You don't see any of it on the screen yet. You can as well ignore. The motivation comes from this simple example. And this is the same word that goes into convolutional neural nets. Quite often people might talk about those neural nets without even knowing what's a convolution. So you will also have that advantage after this course. You would know what that means. Okay, very good. Okay, so it starts from a very simple question. Suppose I got two dice. I'm rolling them both and summing the number I got off of them. Okay, now I'll get a number between smallest 2, biggest 12. Very good. And what is the probability of taking those numbers? Here's the diagram. Taking 2 means you get 1, 1. This happens with 1/6, 1/6, 1 out of a 36. But if you start going like in the middle, the probability starts increasing. Why? Well, think about like what's the probability of getting 7? There are all the options written here, 1 to 6, 2 to 5, goes up to 6 to 1. And you need to think about all these options, sum up the probabilities, and you got 6/36. Okay. Now, we want to have a kind of a more systematic way to think about this. I got 2 random variables. I sum them. What do I get out of it? Maybe summing might look a little strange to you, but I'm sure you will agree if I would do sum and divide by 2, like taking average, this would be very natural, right? So I have 2 random variables. How does the average random variable look like? Okay. To get to that average, let's start from just sum and try to see how that works. It, in general, works like this. This was discrete. The same thing works over discrete and continuous, exact same idea, okay? What do? You look at the density of a number, say S, multiplied with the density of t minus s if you're looking at t, then integrated over all possible numbers s. How does it relate to picture above? Let's look together. Suppose you're looking at the thing in the middle. This number s will go from 1 up to 6. And your density in the discrete case is literally the probability, 1 out of a 6, times 1 out of a 6 for the second dice. If s is 1, 7 minus 1, 6. So this is the first thing right here. And you'll go all the way up, okay? If it is continuous, think about all the values your first random variable could take. And the second random variable should be completing it to the value t you're looking for. Multiply those densities. Since it is continuous, instead of summing, you need to integrate over. That's how you get the density of summation random variables. Very kind of intuitive. And this intuitive thing is what's called convolution theorem. When you call it convolution theorem, it sounds very fancy. Okay, but it's not fancy. You just look through all possibilities and sum it up correctly, basically. That's what convolution is. And this integral operation, this is called convolution. Okay. And then they would write in short like this. x1 and x2 convoluted together gave you the sum. And this convolution, this is shorthand for this integral. Okay. When you see a density convolution, another density, that means you're integrating those densities over to create another one. Okay. This is a shorthand for this expression. So far, so good. This is what a convolution is. And in image processing, you will have some patches around your images, and you will start convoluting them. And you'll kind of get an average of those patches. Or you can also do it locally. You can pick a pixel and take a lot of stuff around that pixel and convolute those stuff around it. You're kind of decreasing your precision in a way. You're kind of zooming out. Because what you want to do about an image, you don't want to know everything about it. You want to know if there's an edge there, if there's a big change in density. You don't want to know everything. You just want to detect the features that tells you what you want, right? You want to know if it is a cat or a dog, whatever else you're looking for. That's why convolution is kind of sensible, and there's more to it. We'll talk about it later. Okay, so this is convolution. So it's like an X. So it will look like this, and then an X in the middle usually. Sometimes you might see also a star. If you see that, that's not my fault. Sometimes like literally a star in between. And I think star would be more common. Usually it will be like a circle inside a star. Okay. Sometimes it could be an X2. I would say star is more common. So something like this. Okay. Yeah, that is a shorthand for this integral. An integral is just summing up the stuff. My mental picture for convolution is literally this. Okay. The thing in the middle is that integral. You're going through all possibilities and summing them up. But since you don't want to write this all the time, you create that shorthand. Okay. Now let's keep going. This I think I'll skip over because of time purposes. Here I had a question like, if I take two Gaussians, they are nice. If I do the convolution, what do I get? The answer is you get yet another Gaussian. I'll put this as an exercise. So either you do it by hand or you look it up and learn. So when you take two Gaussians and do this convolution, you get yet another Gaussian. And you literally sum up stuff here. Okay. All right. Now, let's see how many minutes I got. It's getting 9. Okay. I'm going to tell you 2 more things quickly, then I will tell you something called probabilistic PCA, because I try to give at least one algorithm every lecture. We recapped logistic regression today, but it was something we talked about already last lecture. So let me do probabilistic PCA today. Okay, the 2 things I'm going to tell you, they look again fancy, but they're not fancy at all. The first thing is called law of large numbers. What is it? You get a whole bunch of random variables, x1, x2, xn. Large means this n should be like a big number. Okay. And suppose you know their expectation. And you also know their variance. You don't have to literally know. I'm just writing a simple case here. You just need to know their variance is bounded. Like it's not going crazy. It's like bounded by 5, bounded by 10. For simplicity, suppose they're all 1. Okay. Then you take their average, sum them, divide by n. In convolution, we were only summing. Now we're also dividing by n. Okay. Okay. Very good. Then the question is, what happens if I do this? I know what's going to happen to expectation. So sum up their expectations, divide by that n. The number you get will be your new expectation. You expect this guy to have expectation this. Let me write this instead of just saying. So I kind of know this new guy has expectation x. That mu. That's kind of clear. This I know. Okay. Why? Well, because expectation goes very linear. Just sum up, divide, you get your new expectation. Fine. I know what do I expect from this guy in expectation. But that doesn't tell me everything as we show the pictures. But apparently, if your n is big enough, this actually tells you almost everything about this guy. Okay. The probability of this new average random variable just going little tiny epsilon above or below your expectation, this probability goes to 0 as your n grows, in math, they would say goes to infinity. It will never go to infinity, of course, but okay. So that's the law of large numbers. So as you keep adding stuff and dividing to get an average, it starts becoming almost like deterministic. You sample it, you almost always get this number or something just around. That's called law of large numbers. And the reason for this is actually rather simple. The reason is this. Suppose I take a random variable, x, and I multiply it by 5. I got now 5 times x. What happens to expectation? What happens to variance? Expectation gets multiplied by 5. Variance, since that thing has like a square on it, it gets multiplied by 25, okay? Now, what happens here is, when you're dividing by n, the variance gets divided by n squared. So what happens at the end is this, the variance of your new guy if I wouldn't have any n here, this will be like variance of this plus variance of that, up to n. But now I'm dividing by n. It will go like this. N dividing by n has effect n squared. It will be 1 over n. As n grows, your variance is going to 0. What does variance going to 0 mean? It almost behaves like deterministic. That's the reason for law of large numbers. Basically, dividing by n was kind of too aggressive. Okay. It feels very natural, but this is the end result, and this is useful for some stuff. Okay. But now, if I would be dividing by square root of n, here I will get n divided by n, it will be 1. I wouldn't get this crazy effect. Okay. And that's what's going to happen for central limit theorem. Before I go there, any questions about this? Literally, you keep taking a whole bunch of random variables, and you average them over, they start behaving rather deterministic. This does happen. And this is one reason that we are able to predict very complicated systems that includes randomness very precisely. It's very counterintuitive, but think about the gas in this room. All the particles, they're rather random, but we're able to predict a lot of stuff about it because of this kind of effect, okay? When you have a system, there's a whole bunch of randomness coming in, sometimes somehow getting averaged over, it becomes very predictable. For example, what we call temperature is this kind of average. Temperature is some average notion of energy. Okay. Physicists know this really well. They have been predicting this kind of stuff for decades. And I just admire and learn from them, basically. Statistical physics people, they know this stuff really well. Okay, my next thing is called central limit theorem. There, what do? We take, again, a whole bunch of random stuff. Expectations are known, and variance is bounded. Again, you don't have to know it to be 1. As long as you know variance is less than some fixed number, you're fine, okay? This time, we learned our lesson. We are not dividing by n. We are dividing by square root of n. The only reason being, when I compute the variance of this guy, it's going to go like 1 plus 1 plus 1 plus 1, and then divided by square of this and divided by n, 1. It's going to be reasonable variance, okay? Then the question is like, what happens when you do this? And let's be even more careful. If I only sum up, I knew the expectation. The expectation is going to be summation of those. So let me even take out that so that the expectation goes to 0. I can shift. So this is to make the expectation 0. This is to not to be very aggressive with variance. And you expect this random variable to behave somewhat nice, okay? Because you're summing, think about the middle of that dice stuff. It was starting to look like a Gaussian. Let me go back to that picture. You know, doesn't this look literally like a bell curve? So that's what central limit theorem is all about. So here is your central limit theorem. If you do the summation, shifting mean average to 0, and dividing by a reasonable number, you literally end up getting Gaussian. Okay, but this is something amazing. I did not assume almost anything at all about this random stuff. I just said expectation known, variance bounded. That's all. It could be whatever random variable you like. But if you have enough of them, you end up getting a Gaussian of it. This is central limit theorem. Okay, this is what I was trying to warn you about. So you will go to some meetings and they'll say, by central limit theorem, we have enough data, let's just use Gaussian. Okay? So it has truth in it, but it goes to Gaussian when your n goes to infinity, which never happens in practice. This is an asymptotic statement. So there is truth in using Gaussian to model very large discrete stuff. If n is big enough, this will literally start looking like Gaussian. But if you are very serious about your modeling, you need to ask, how big is my n? How close am I to Gaussian actually? Okay. For this, there is about a lot of results. Just 1 second, I'll get to that. If you want to be more serious about this, there are a lot of results already built up for you. Probably theorists have been working on this for quite a long time. Okay. And those are called Berry-Essen theorem or Berry-Essen type theorem. You just need to Google these two names. And then you will get a more quantitative version of central limit theorem. It will tell you for a given n, how close are you to Gaussian actually. It will be much more precise than an asymptotic state. Okay? Yes, Jack, what was the question?
Yeah.
No, it only depends on n. That was the amazing part of central limit theorem. As long as variance is bounded, you get your Gaussian. Yeah. It's a deep result. Okay, I'm not trying to underplay that. I'm just trying to make you careful when people use it in practice. Yeah, when you look up this theorem, you will get the precise statement about it. It will not only look up the variance, it will also look up the third moment. It will look at expectation of x1 to the third. There's many variations of this. People have kept improving it. But any version is good enough to be serious. Yes. Sorry. Very good. Let me give you some exercises today. Very simple stuff can be unbounded. Any other questions? Very good question, though. Yes. Yeah, I mean, as I said, I just presented in the nicest case. As long as you know variances are all bounded by some number, you're fine. They don't have to be equal to each other as well. It's just like variance is bounded, so my random variables are not crazy. That's all we need to know. Yeah. Like, for example, something called Cauchy, very common random variable, it's unbounded. I can give you examples. Let me give at least one today after the lecture. So it was a very good question. Okay, now I want to use the last 6 minutes to talk about probabilistic PCA. All right, so probabilistic PCA is kind of an addition to PCA we have seen. How does that go? So what was PCA? You get your data, and then you look at either singular value decomposition or whatever else you use. You find the directions that seems to preserve most of the structure of your data, and how many directions is up to you to pick. We had data living in N features, and we were picking D features, and D is up to you to pick. That was PCA, okay? And we have a very nice notebook about PCA on our canvas. However, this is like good, but very restricted in a way. It's only working for the data you gave to it, and it's only reducing dimension of that data, and that's it. If you give to same PCA a different data, who knows what's going to happen? And if you ask to PCA, can you give me like a typical of my data? No, completely muted. Okay, PCA is good, but it only does what it does. Now, since we have PCA, let's try to play with it a little bit and see if we can get anything out of it that is either generalizable or like generative. So what does generalization or generalizable mean? It means whatever you created works with some data it has not seen before. PCA has no such ability. Generative means when you ask it to give me a sample of the type of data I'm dealing with, create one, it can generate one for you. That's what generative means, okay? All right. Now, probabilistic PCA, also sometimes called sensible PCA. Don't ask me why. People called it, I don't know why. It's a very simple generative model that you can build off of your PCA. How does it go? Let's say this was my data points, capital N of them with N features. And in your PCA, you picked D to be your dimensional reduction. And now your intuitive picture for this, specifically when you want to be generative, this was like my data's hidden real dimension. It looked like N features, but if I did my PCA right, it's actually a D-dimensional thing in reality somehow. My image data had thousands of pixels in it, but when I reduced the dimension to say 300, it was still working perfectly fine. So you're thinking, in reality, this thing is maybe 300 dimensional, okay? So like intuitively. So in statistics literature or in machine learning also, this hidden dimension will be called latent space. Latent literally means hidden in Latin, okay? And you would think about a latent variable living in that latent space. And you would think this hidden guy is actually controlling what's going on, but I don't see it. It's hidden. Okay? That's kind of the intuitive picture. And then the probabilistic PCA goes like this. You would assume the hidden guy, let's assume it's simple. The hidden guy is just, say, Gaussian with covariance matrix identity. Okay? Suppose the thing that is living in that smaller dimension that I don't see, suppose the nicest thing possible about it, okay? This is my prior assumption. This is my hidden guy. Now, my data conditioned on my hidden guy will look like some matrix multiplied with that hidden thing, shifted, okay? This was a Gaussian, multiply your Gaussian with a matrix, shifted a little bit. That's your expectation for your data. And now give it some juice, also known as some noise, so that your data can move around a little bit. This is literally your probabilistic PCA model. The data you are seeing is actually a Gaussian. It didn't tell you that it's a Gaussian, but it's a Gaussian multiplied with a matrix, shifted a little bit and added some variance to it. And then if you work this out, your data is supposed to be centered at here. This was the conditional probability. If you look at what this actually gives you for data, centered here with this covariance matrix, okay? This, as I said, is a very simple generative model, but it is now generated. If you ask this model, give me a typical data, it will sample from this and give you data, okay? And now we have a notebook that I'll upload to Canvas today. It will do this on image data. So it will try to give you some simple Gaussian that will look like face of a person, okay? If this looks like a face at all, it is like a miracle, right? It's like a Gaussian, what the heck, right? But it actually does look a little bit like a face. You will see from the notebook. So this is not too simple. It is sometimes useful. And the point of it is it's generated, okay? And that's it for today. Thank you so much. Exactly. That W there is exactly the W you get in PCA. Yeah, that's exactly the projection W we got back then. That's why some statistics people call this sensible PCA. For them, I guess this makes more sense. Okay. All right. Yeah. If you want to ask questions, I'm here.